10.7 elastic deformation. I'm sure you'll like this chapter because I really do. It's really simple. So, before we get into this, I kind of want to provide some historical context. Young's modulus was discovered around the 1800s, and actually, contrary to what you would think, it's not um, a person named Young who initially discovered it. I think it was Leonhard Euler, one of the smartest people in mathematics. Um, so that's, I guess, the history behind it. So all solids have atomic microscopic springs. In chemistry, you'll learn that there's an internuclear distance that minimizes potential energy, uh, such that um, such that it's the most stable at that state. So the same way, the solids have a state that it wants to be in. So when you push on that solid, the solid wants to go back to its original form. And it does because we are saying that it's elastic deformation, essentially meaning that the object will come back to its original position. Also, I should mention Euler because I'm going to do a proof on the e to the x derivative, so that's pretty interesting. So the formula is F equals delta. You know what? I'll just write it out because that's in English and I forgot to put it into mathematics. F equals Y. It kind of looks like the gamma function. And then delta L0 times area. So before we get on further, I'm going to explain this mathematically. Um, so the change in length divided by initial length is essentially the ratio in which the object changes compared to the initial length. And the area is the area of the surface. So they'll typically use a rod, but it doesn't have to be a rod. But we'll get to that a little bit later. So Y equals stress over strain, which equals pressure over fractional change in length. All that it's talking about is the units. Y equals pressures divided by fractional change in length. So that would be fractional change in length would be delta L over delta O, or L0. But guess what? It's interesting. The reason being is because LO and LO will cancel out. LO and L that will cancel out, leaving us pressure times area. And I'm sure you guys know that pressure is force divided by area. If you don't, then now you do. And now we realize that A's cancel out, giving us force. So somehow some pretty smart people just figured that out. And I love how simple this formula is because you would think that compression would be a lot more difficult than it is. So if you look inside atomic or objects at an atomic level, you'll see that they're kind of arranged like this, where they'll have springs like that. So when you compress it, it'll get a little bit shorter, maybe like that. But what it wants to do is return to its original state, and that's why it's elastic, because it usually will. Um, Things like rubber, stuff like that, are typically more elastic. So let's go over this formula again, because there's something I want to show you, and what I want to show you is I want to show you what the variables that are changing are. Notice that y is a proportionality constant, which essentially is the slope of the function. So that will just be m. And area is constants. So essentially, m and a come together to make the slope. So we'll just say mc delta L over LO. But technically, this can just be denoted as an arbitrary constant m. So that means the ratio of the length to the initial length is proportional to the amount of force that is provided. That's not mass, by the way, just to not get you confused. So that's pretty smart. But let's see what it means in a visual scale. So we have a rod right here. And let's say that this is L0. So let's just say it's standing on a wall, and that's just the rod in its natural length. Now let's say we push the rod inwards. Also, this works for elastic collisions, or not elastic collisions, for stretching, not just compression here that I'm doing. So this is LO, but we also have a delta L. Delta L is going to be positive here. Or actually, since we're doing it on the thing, it can also be negative. So the formula we're going to apply is F equals Young's modulus delta L over LO. So now we have all the variables and area. But notice area is just this, so we're just gonna say area, and then basically a perfect circle, so that's pi r squared. So we can rewrite this as y, well those would just be arbitrary constants, times pi r squared, and that will give you the force of how much you compressed it, much like a spring. So pretty interesting stuff there. Forgot what I was gonna say. Yeah, so this can also be a negative force because you're applying a negative force to the object. And when you're decompressing it, you would apply positive force, or if you're stretching it, essentially. So, pretty interesting stuff there. So shear deformation is a little bit different, and what happens, I'll just read it for you. It's a shape change, not a length change. So the formula is the exact same logic with different variables, because there's the proportionality constant, it's all that. Same thing. So let's take a book like this. I'm not the best drawer, so I'm just going to draw that. And let's say that we apply a force simply to the top of the book, a frictional force. So that would mean like me putting my hand on top of the book and sliding it somewhere. The book will look something like this because only some of the book is getting changed. Now the formula here that we're going to want to apply is F equals, and they use S. So I don't know why they changed the variable names around because I would think that's quite confusing. S to denote that it's shear modulus that we're dealing with here. And it would again be delta L divided by LO times area. But the interesting thing here is that I use a different logic, or I guess a different way to put this, S delta X over H over A. The reason being H is essentially constant here. So height is constant, and delta X is the change in position here. So if we're doing it this way, it's going to be positive force. This is going to the right side. So it's the same exact thing. And the area is just going to be the top of the book, which a book is typically rectangular, so it would just be length times width. So S delta L, or S delta X, over the height times LW. And yeah, that's shear deformation. Now the last one is pretty interesting as well because we get into volumetric stuff. And also, I mean, this would be pretty easy to figure out because it's a linear function. They're proportional, so it's a linear relationship. But we get into bulk modulus. So, as I've told you, pressure equals force divided by area. Essentially, how much force you are applying per unit of area. So the change in pressure is going to be equal to negative B delta V over VO. So let me explain the logic behind this. And the logic behind this is pretty simple. So delta V is VF minus VO. But when we get to something like volumetric deformation, you're typically putting something in something that compresses it in all lengths. So let's say you put a submarine into water. Let's assume that submarine is perfectly circular. That water is crushing it all throughout. There's high water pressure in the thing. So typically the volume is always going to be lower than the initial volume. So delta V will always pretty much be negative, which is interesting because we have a negative here. So what happens is we can cross these negatives out to give us a positive change in pressure, which is what we want typically. So large B means it's hard to compress because delta P over B times VO would equal delta V. And notice here that the higher B is, it's in the denominator, making this entire term smaller. Pretty easy logical stuff. So that's all of that, and I'm going to be doing an Euler's derivative proof for later, so it's interesting.